with that, we will now move on to maybe, one of the most important algorithms, and indeed the content of homework 4, which is BFS, which is breadth first search. Okay, so BFS, breadth first search. So BFS is an algorithm to traverse a graph. So what does traverse mean? It means visit all edges and vertices. Just as remember that in trees, we have these notions of tree traversals, the in-order, pre-order, and post-order, which are ways of visiting all the vertices of a tree. Now we have an algorithm that visits all the vertices of the graph. But actually, even though it's just an algorithm, it actually, BFS more broadly can be thought of as a technique to solve many graph problems. So there are many different graph problems. Just like for test 4, you had these lists of different problems to solve. I'm going to give you a list of problems on graphs, and BFS is the technique that often solves most of them. To keep this discussion somewhat easier, I'm going to think of G as undirected and simple. Now, when things are directed, BFS pretty much works the same way, but the notation gets a little more complicated, so I'm going to spare you that in the first discussion. We can talk a little bit about that later. Okay? So someone in the chat says, getting a little ahead. Are we going to look at DFS as well? Yes. My hope is, we have, we have 5 lectures left. After this, we have 4 lectures left. Because the last lecture I don't teach. I don't teach generically in the last lecture. So I will cover BFS and DFS. And I'll also try to cover shortest path algorithms like Dijkstra's algorithm. All right. Before we get to what BFS does, it's helpful to understand what the output of BFS is. So I'm going to state a few definitions. So we're going to do a little bit of a dive into more mathematical notions in graph theory, understand what the output of BFS is, and then we can discuss the algorithm, which is actually not very complicated. So I'll say a vertex U is connected to vertex V if there exists a path of edges from U to V. So what this means is U is connected to V if you're going to have some sequence of edges like this. So there's some path between them. That's what it means for U to be connected to V. Okay, that's what it means to be connected. Now we'll define a notion of shortest path distance. So between any two connected vertices UV, the shortest path distance, which I'll denote D of UV. So unfortunately, let me not call it, should I use No, D looks like degree. I'm just going to refer to that as dist UV. Okay, I'm going to call it dist of UV. The shortest path distance is the length in edges of the shortest path between U and V. Right? So between U and V that are connected, maybe there are many different paths. But maybe there's just this one path of length 2. Then I'll say the dist of U and V is equal to 2. Right? That's what it means for the shortest path distance. Now,
what is if there's no connection?
If there's no connection, then conventionally you just say it's infinity. If UV are disconnected. This is just conventional. That's why in the definition, I sort of impose that they're both connected. They're connected. And so when things are directed, usually your paths have to have a direction. Right? Your paths have to go in one direction. And that's why it's easier to think about undirected graphs for the sake of this discussion. Okay. All right. So let's just pause for a couple minutes here, and I can take any questions that you have. You can stretch. And then after that, I'll tell you about the output of breadth first search. Excuse me.
Hey, Professor.
Yes.
Will class be online again on Thursday, or is that to be determined still?
That's to be determined. I want to see what the situation is, and then I'll determine accordingly.
Okay, thank you.
I mean, I don't know. I'm actually happy to do whatever you prefer. So maybe now that I can poll you, that's something I can do. So let me just ask you. On Thursday, would you prefer to have class in person is A and B is over Zoom? So in person is A and B is over Zoom. What is your preference? A is in person, B is over Zoom, and C is, I don't understand the question, which I guess one person didn't understand. So
I suppose I don't care.
Yeah, I don't care would also be fine, I guess. Okay, so yeah, I guess there's a C of I don't care. A is in person, B is over Zoom. Doesn't it depend on the picket line, as someone says? Yes, the problem is it's a little hard to predict the picket line ahead of time. And so obviously if the strike is called off, then I'm going to hold it in person. But I'm assuming the strike is not going to get called off in the next couple of days. So that's the assumption, assuming that, the things are still there. So actually it seems that, because today had a lot more people than yesterday. Yeah, no, I realized that actually the strike is picking up. And so that's one of the reasons why I decided to hold it. So actually it turns out that, well, I can show you at this point. I actually share the results. You can see what's there. So again, it seems like, people would prefer to have it over Zoom, but there's a sizable minority that want it in person. And there's, of course, the 16% don't cares. So, yeah, so, I'll make a decision on Wednesday. Let's make a decision on Wednesday. Yeah, I am sympathetic to those who don't live on campus, and I know that the buses weren't running, so it is a bit of a pain. The sections are going to be in person because I want the tests to be in person, and also the tests are at pretty strange times, so I doubt that you'll have trouble getting on campus. Like they're at the night 7 o'clock, I doubt that picketing is going to be an issue. As someone said, I don't think strikers explicitly prevent people from getting on campus, but they'll often be crossing the streets. And so what that happens is it slows down traffic, and then it basically, it creates problems. I'm surprised by attendance though. Like, so even over Zoom, there are about 66 people, which is about short of a third of attendance. So, funnily enough, during COVID times when I was teaching over person, that was when I had the highest attendance. Like, I would get almost 75% attendance because I guess people had nothing better to do than actually come to class. Like, nobody had a life anymore, so they were actually attending class. Someone said maybe they just watch on Yuja, which is I guess that is true. But I don't know. I would assume, but definitely coming to class is different from watching it on Yuja. I'm actually surprised that so many, what is really ironic, I feel, is that the department and the staff, they go through a lot of trouble trying to schedule like the right size of the lecture hall to accommodate all the students and everything. And then it turns out that the attendance is only like 30-40%. And so it's like, why bother? Like, we might as well just schedule things in a much smaller room, use less resources, because most of the students aren't going to show up anyway.
Is it consistent from class to class, like from quarter to quarter?
The attendance being less than 50%?
Well, the attendance being anything.
I think 50. I have rarely seen it be more than 50%, like midway through the quarter. Whenever I've taught 101 or I've taught precursors to this course, it's actually been that's what it's been consistently. Like, I'm not offended personally in any way. It's just that I feel that a lot of effort goes into sort of having this like, you don't know how much trouble that people have in scheduling in the lecture halls, and we need to find a big enough lecture hall to accommodate everyone. And I keep saying, but we don't need to accommodate everyone because they're not going to come. Of course, if someone says with COVID in mind, yeah, it could be that some people are coming. COVID is there, but even before COVID, attendance was routinely like 40-50% unless it was forced. And I don't believe in forcing attendance.
So you didn't have a 50% drop rate?
No, it's not a 50% drop rate, no. So the class is still, we still have more than 190 students. More than 190 students who are enrolled and who are doing the assignments and who are, I guess, submitting and going to the tests and whatnot. But it's just attendance. Yeah. All right. So, sorry, go on.
Viewing rate.
Sorry?
What is the viewing rate of the videos then?
I don't know. I haven't seen it I haven't checked. I don't know if Yuja records those stats. I've been a little lazy this quarter putting things on YouTube that quickly. Partly because it's all available on Yuja, and then I will put it all on YouTube though. Yeah. Okay, good. So let's go into BFS now. So I want to talk about BFS as an argument. So I'm going to think of this procedure as having a single argument S. So it's a single argument. And S is what's called a source vertex. So, excuse me, the output of BFSS is called a shortest path tree rooted at S. This is what the output is. So what this means is it's a tree with S as the root. And I want to emphasize this is not a binary tree. So a tree simply means that you have a vertex has got some children, which has some further children. So some of these might just have one child. It could just be one child having one child, and then some of them have many children, so on and so forth. This is the output. This is the output. Now the tree has following properties. So it has two key properties. One is all vertices connected. So I should say, this is a tree with S as the root. The nodes of the tree are vertices in the graph, right? So all of these are going to be vertices, but I don't want to confuse. Well, okay, so, and the edges are edges. So both the edges and vertices are from the graph. So all the vertices connected to S appear in this tree exactly once. And two, all paths. Okay, so let me sort of restate this more carefully. I'll say for every V in the tree, so if you take some V in the tree, it could be a leaf or it could be an internal node. The path from V to S in the tree is a shortest path in the original graph. So what this means is if I look at V and I follow up the tree and I get this path, I look at this and I follow up this path, these are actually shortest paths of the original graph. So this tree is actually called a subgraph. It is a subtree. It's a subgraph, which just means it's got a bunch of edges and vertices from the original graph. But it has this remarkable property that all the paths that go to S, not between any other pair of vertices, but any path that goes to S. So if you keep following this tree up, you end up with a shortest path from V to S. So this only gives the shortest paths to or from S. And I say to or from because it's undirected, so it doesn't matter. But if it was directed, then you would get shortest paths from S to every vertex. Okay? Excuse me. So what this solves is, suppose you have a problem, the following problem, which is the routing problem, which is given S. Suppose for all V, you want to compute the distance from S to V. Then BFS of S solves this problem. Okay, so is this clear? Are there any questions about what it means to be a shortest path tree? So this is really important. Do not confuse this with a binary search tree or any other kind of tree that you've seen in the course so far. This is not binary. The nodes are labeled with vertices of the graph. So basically you can look at each of these is just a vertex of the graph. And each path over here is a shortest path, the path from V to S, not paths in between other vertices. Not paths in between other vertices. So I could get a path that goes from this vertex to this vertex, like looking at this and this. That is not a shortest path. I'm not giving any guarantees about that. Only paths that start at a vertex follow up their parents all the way to the root, to S. So another way to think of it is to get a shortest path from any vertex to S, you keep following the parent pointers and you'll end up at a path that is a shortest path. Okay, any questions at this point?
So how is the shortest path like not from like S to like that like second node?
So I'm sorry, from here to here?
The one on the left.
This one?
Oh, the next one. No, the one like the one on the right after that. Like the second branch.
This one.
Yeah, that one.
This is also shortest path.
But like,
I just didn't draw it, but this is also shortest path.
so
And
like,
this is
wouldn't there be just one shortest path?
No, there's only no. So there are shortest paths from S to all other vertices of the graph. Remember, the shortest path is in between two vertices. So it's between S and V for all V. Think of it as you have this graph. You have this one source vertex, and you want the shortest path from here to every other vertex. And BFS of S is going to give you that information. Does that make sense?
Oh, okay, yeah.
Right? So it's like, don't think of it. So think of it as, you're at a social network. Actually, you'd be surprised how much this information is used in your recommendation feeds for any social network. Essentially, a way that they find recommendations in social networks is they construct a graph, they put you at the graph, and they say, find all paths from you, shortest paths from you. So someone asks, will you be showing us how to implement BFS? Oh, yes, I will. I will show you how to implement BFS, and then you will implement BFS for homework 4 on a large data set of actors that I scraped from IMDb. So yes, you're going to see how to do BFS. Okay. Now I did start a little late, so I'm going to go a little bit over time today. Because I'd like to complete some amount of this before I finish. All right. So if there are no more questions, then I want to tell you about how BFS is implemented. Okay. So remember, we're discussing the procedure BFS of S. The vertex set, remember, is labeled 1 to n. And this is going to be quite convenient. So what BFS maintains two arrays, and these are really can be thought of as bitmaps. Well, no, I shouldn't say that. Ignore that. And a queue called capital Q. Okay, so this is really important. This queue, remember, a queue is first in, first out, right? Excuse me. So what are these two arrays? So these two arrays are going to have names. One is called predecessor. Both of these array is indexed by V. And the predecessor of V, when you finish BFS, is going to be equal to the parent of V in the shortest path tree. So the predecessor array is essentially storing this. You can think of predecessor as just the parent, but it's called predecessor for a reason, and you'll see why. The predecessor array is essentially just going to store the tree, because to store a tree, all you need to store is your parent, right? If every vertex knows who its parent is, then that basically gives you the tree. So all you need is the predecessor array over here. That's to store the shortest path tree. Then there is going to be another array called visited. Okay. And this is a Boolean array. It's a Boolean array, again indexed by V. So visited V, excuse me, is going to be true if BFS S visits V, and false if it doesn't visit V. So what this means is, the way to think of what BFS is going to do is BFS is going to do what's called a crawl or a traversal. Okay, so crawl. What this means is it's going to start walking on certain paths. And as it walks, it's going to visit a bunch of vertices. And whatever is visited is labeled true. What is not visited is labeled false. And BFS is simply going to just update these three data structures: the queue, the predecessor array, and the visited array. Okay? So I'll take a quick pause here. Any questions? Are there
Question.
any? Yes, go ahead.
I don't quite get if V is like the index or the value itself. Is the index of the array represent the value of the array? So like the length of the array is like the maximum value. I'm not following that.
Sorry, where? Which part? This?
Like basically, I don't understand if V is an index or a value.
Capital V is a set. Capital V is a set. Little v is an index. Because little v is some element from 1 to n. So little v is like an int. It's an int or it's an unsigned int from 1 to n. And so predecessor of v simply means like, it's the array at that index.
It's just like you put an arbitrary index into an array called predecessor, and but what does it store the parent of?
Of v,
like
that vertex.
Okay, but it's just an index, so it's just a number.
Yeah, but the number is the vertex. The vertex is labeled as a number.
Oh, got it. Okay, so it's the index. It's a parallel array. Is that what you're saying?
I don't understand. So the thing is, the array. So think of the vertex set is 1 to n, right? So these are the labels of the vertices. But the label can also be interpreted as an index.
Yeah. So the length of capital V is the same as the length of predecessor. Both those arrays are the same length. Okay, cool.
Exactly. Both of these arrays have length n. Right? Both of these arrays have length n. Okay, technically you might do n plus 1 because you want to index from 0 and whatever. But ignoring those off by 1 things, which I don't want to worry about, you have a set of vertices. Someone says, will we be able to find the lecture papers on the website? Of course, I will scan everything and put it up as usual. Someone asked, are there any invariants that these graphs must maintain other than the vertices and edges? I'm not entirely sure what your question means.
Like for BSTs, like they have to maintain, like it has to have, like your left child is going to be less than the root,
Good question. No. For undirected graphs, no. Okay, so I see. The only invariant that an undirected graph maintains that if U is a neighbor of V, then V is a neighbor of U. That's it. But other than that, there's nothing else. There's no invariant on the labels for a graph. Usually there are specific kinds of graphs that maintain specific kinds of variants, but in this case, there's nothing. Okay, so let me, sketch out the pseudocode for BFS of S, because we can write it down without too much effort. So the first is we'll initialize the Q with S. So the Q is going to have this vertex S. The second is the predecessor array is initialized arg is initialized to all null. We're storing pointers. We're storing indices. Sorry, we're storing parents, and all the parents are initially null. And visited is all false. So this is how we begin everything, except we're just going to set visited of S to be true. Okay, so visited is all false except for visited S, which is true. Okay, so this is where the real work happens. We'll say while the Q is non-empty. What this means is while the Q has something in it. Now, initially we put S into the Q, so the Q has something in it to start off with. we will dequeue from the queue. That's going to be U. Then we are going to do a traversal step. So we say for every vertex in the neighborhood of V. Okay, this is where we traverse the adjacency list, right? Because in the adjacency list, you can find all the neighbors. Then we'll say if visited of V is false, which means you have not seen V before, then you're going to do 3 steps. Step 1 is you're going to say, well, now I've visited V. So visited of V is true. I'm going to say, where did I visit V from? I visited V from U because I'm looking at the neighbors of U. So I set the predecessor. And then the third is I'm going to now enqueue. So I'll do q dot enqueue. Maybe I'll do q dot dequeue or whatever. Sorry, I'm just going to write this out in this way and then it should be clear. I'm going to enqueue V. So V is added to the queue. This is BFS, right? And then there's a little bit more we need to do for BFS on the whole graph, but this is the most important part of it. This is like all the action happening here. So let me just walk over this again. BFS starting from a source vertex. We're going to initialize the queue with S. We're going to initialize predecessor to be null and visited to be all false, except for visited S, which is true. Excuse me. Now, while the queue is non-empty, we're going to dequeue U. So now I'm going to draw a picture here. So this is U. Now, everything that has been visited, I'm going to color in. Okay, so this has some neighbors. So you're going to you're going to go through all the neighbors. These are all the V's. Now, some of these may have been already visited some other way. So everything that is visited, I'm shading, right? So that means this is visited. So for every V, I'm going to go through all the V's. And if it's already been visited, don't do anything. But if it has not been visited, for example, this V has not been visited, then what I do is I set visited to be true. So I'm going to color that off. I'm going to make the predecessor of V be U. So remember, the predecessor is storing the tree because that's the parent. The predecessor is storing the tree. So in that shortest path tree that I have, I've essentially set V parent to be U in the shortest path tree. And then I add V to the queue. So there's this queue of vertices, right, which are being processed. And so let's say this is the front and this is the back. I'm going to add V to the queue. Like it's going to go to the queue. And once it's in the queue, eventually it's going to get dequeued. And eventually BFS is going to start this entire process looking at the neighbors of V. Okay? So this is the pseudocode for BFS. Any question? I mean, why this works is not entirely clear. And I will talk in the next lecture. I'll tell you more about what BFS achieves.
So when you're storing the predecessor of V, like setting it as U, like I'm assuming like on the diagram you just drew, like there's like another imagine there's like other nodes in between U and V. Is that why you're setting it to U?
You mean, yeah, there could be, maybe there are many possible paths between U and V. There's a lot of other stuff going on.
Okay.
Right? There's a lot of other stuff going on. But what this says is because you visited V from you, like the first time you saw V was through you. Predecessor is marking that. It says, oh, the first time I saw V was from you. So that's what the predecessor means. It turns out that this is giving you information about the shortest path. Now, this is not obvious. But this is what's like, that's sort of the magic of BFS. That's what is going to happen.
Got it. Okay, thank you.
Any other questions? So someone said next lecture in class or Zoom. Again, as I said, I will make that decision, maybe tomorrow, seeing what the situation is like. If I think there's any risk of traffic problems, then I will do this over Zoom again. But sections I would like to hold. Sections will be held.
So we correct the homework too and submit it? So are you going to correct it or we wait for TA to
Yeah, we wait for TAs. I mean, it is a little late for homework too.
Okay.
But yeah, so I again, like this is pretty late in the quarter. Homework 3 has already been submitted.
Yeah.
So yeah, but it would be done by a TA. So I'll let it go this time. But in general, please try to, let's not hold off regrades that long. Yeah.
Thank you.
Oh, sorry, I had a question, Professor.
Yes.
So basically with the test today for Tuesday, it's still going on as planned, right?
I'm sorry, say it again?
Oh, the test for tonight at 7.
No, it's not. No, tests for Monday and Tuesday are canceled. Yesterday and today, both are canceled.
Okay.
Canceled? Well, they're not canceled. They're postponed. I'm sorry.
Postponed, yeah.
Tests for Monday and Tuesday are postponed to next week. Wednesday, Thursday, and Friday will continue as planned.
Okay.
Okay?
Okay, thanks.
The homework to regrade, yes, next Monday. But next Monday is the last, is the last chance for homework to regrades. Okay, so any questions? If there are, I'll wait for a few minutes. Yes, I will be holding open office hours, at 12. But I'd like to answer if there are any questions about this. I'll wait for a few minutes. Otherwise, the lecture is over. And in the next lecture, what I will do is I will talk more about BFS, explain why it works, and hopefully that should give you enough of a picture of BFS.
So basically, you're essentially like with that diagram you made. So you're finding all the neighbors of that current you are on, and then you're in-queuing that, and then like let's say you get all the ones you drew. So when you're dequeuing, you're getting the what's it called? The latest one?
No, so you're getting the earliest one. So think of
earliest
the queue.
one, yeah.
The queue has a bunch of things in it. So maybe the front of the queue was you.
Yeah.
And you're going to remove you. That's what the dequeue does. And then the neighbors of you are going to go at the end of the queue.
Right.
So
Yeah, because you're in-queuing.
You're in-queuing. They're only going to get processed after all the other things in the queue get processed.
Got it. So that first neighbor we find, that will be the one that's processed first.
That will be processed earliest, exactly.
Okay.
But it's important to note that it's going to be processed only after whatever is already in the queue gets processed.
Right.
Because there are a bunch of things that are already sitting in the queue. So what happens at this stage is that so maybe to give you an example, there's V, there's W, and there's X. So all of these are going to get visited and they're going to end up at the end of the queue. So V will go, then W, then X, right? And then this is going to get processed. So as soon as this gets processed, this adds a bunch of other things to the queue.
Oh.
And then, so by the time you come to V, there are many things in the queue. So V's neighbors are going to go only at the end.
I see.
I will make a comment here that instead of a queue, if you put a stack, then this becomes depth first search.
Oh, okay.
So actually that I will talk about, maybe not the next, but the lecture after that. Someone says, so all of U's neighbors will be visited before it starts to visit V's neighbors. Exactly. Even not just visit, but the traversal. Like this traversal step happens for all the neighbors of V before it happens to all the neighbors of U before it happens to the neighbors of V. Exactly. As you point out, if it's a tree with a root on top, it does go layer by layer. So that's why it's called breadth first search. And so it's a little tricky, but you then formally prove that what you get out of this is a shortest path tree.
I see. Okay, that makes sense. Okay, thank you.
Excuse me.
Wait, do we initialize all vertices in the trees with like their neighbors before we even run this process?
No, so the tree is actually, imagine, is all null.
Mm-hmm.
So the initial tree is like it's empty. There are no edges in the tree. Every time you visit a vertex, you're adding an edge to the tree.
But how do we know, like, for like line II, like how do we know like which V's are actually next to the neighbors?
Oh, this is because this is stored as an adjacency list. So I want you to distinguish between two things. There is the graph, which is your input, and there is the tree that you're building.
I see. So we already have the graph.
You already have the graph, but you're building the shortest path tree.
Okay, that makes sense. Thank you.
Yeah. So what this is doing, maybe to add, is this step is really adding an edge to the tree. To the tree. Not to the graph, but to the shortest path tree.
Okay, thank you.
So what is stack? It would be the latest one would be considered
exactly
first.
The latest. That's why it's called depth first, because as soon as it adds someone, it just follows them.
I see.
But this is breadth first because what it does is it actually, everybody gets their turn first, then V will get processed. If you make it a stack, then actually you will not get shortest path information. You'll still get a tree, but it's a very different kind of tree.
Okay, so it's almost like stack is like everyone goes into the line, but the person at the end actually gets to go first.
Yeah, I mean, it's essentially it's last in, first out, right?
Yeah.
So it's LIFO versus FIFO. And what is really important is that because this is first in, first out, the tree that you get is the shortest path tree.
Got it. The shortest path tree. Okay.
Again, this is not obvious why it's a shortest path tree. I'll talk about this in the next lecture. But the shortest path tree emerges because you're using a first in, first out queue.
Okay. Thank you.
All right. So if there are no more questions, I'm going to end the lecture, and I will upload the slides, and I will run the autograder. All right. Bye, everyone.